We talked about the law of conservation of matter. Now we're going to talk about the law of conservation of energy. This is called the first law of thermodynamics in physics. This is the first law of thermodynamics. The energy of a system is constant. What you start out, you end up with the same amount of energy. So the total energy of a system, of a closed system, which will be like the Earth or the universe, is constant. Okay, what does this mean? Okay, here's an example of the first law of thermodynamics, law of conservation of energy. The sun gives off light waves that penetrate the atmosphere, and a plant can absorb that sunlight energy and turn it into, by the process of photosynthesis, turn it into glucose energy. Now, take all the light that hits this plant is not used to make food. Some of it turns to heat, some of it's reflected, but the total energy of the sunlight, okay, so here's the sunlight hitting the plant. It will be converted into, by photosynthesis, into chemical energy and glucose. That's what the plant uses the sunlight's energy to do, plus heat. Okay, so the total sunlight hitting the plant, some of it's used as energy and some of it is used as heat, and some of it is just reflected off the plant. Okay, so all we're saying is energy that you start out with has to equal the energy that you end up with in a closed system. Or we can look at the whole Earth instead of just the plant. So sunlight hits the Earth during the daytime. Much of that sunlight is turned to heat as the rays of light hit objects. I mean, you can feel it when you walk outside, touch your car, it's hot. So light is hitting the objects on the Earth, let's say Earth, and most of it's turning into heat. Some is reflected light, which eventually turns into heat. Some of it is absorbed. Some of that heat is dissipated to the air and then back to outer space. Some of that heat heats up the air and water and land, and a little bit of it's made. Some of that sunlight is converted into food by photosynthesizing algae and plants. The great majority of that sunlight that hits the Earth turns into heat. But the first law states that none of the original energy that hits the Earth is lost. It's changed into other forms. It's changed into heat. It's changed into chemical energy and glucose, but none of it's lost. So if you started out with 100 units of sunlight, it hits the earth. 80 units of that sunlight will turn into heat. 5 units of that sunlight will turn into glucose that is formed by plants or algae by photosynthesis. And then the rest percent is reflected light that will eventually turn into heat as well. So none of what you start with of energy is lost or created. Okay, before I talk about the second law of thermodynamics, let's talk about what we call free energy. Okay, free energy, I don't know where they get the word free, but free energy is the energy that can be used to do work. Energy that can be used to do work. So if you eat a sandwich, the amount of energy that you have from the chemical bonds in the food of the sandwich that's released, and that can turn into ATP, which you can use to do anything that your body needs energy for, like muscle motion, thinking, nerve impulses, moving molecules through active transport, protein pump. Now, heat is wasted energy, dissipated energy, spread out energy. It can't be used. Heat is the opposite of free energy. Heat is energy that cannot be used. Can't be used to do work. It's dissipated. It's spread out. It's released into the surroundings. Okay, so heat is not equal to free energy. So whenever energy is used, you can get free energy, but you also get a lot of heat wasted. This is the second law of thermodynamics. Whenever energy is used, some of that energy is wasted as heat. Whenever something uses energy to do work, the energy input is always going to be greater than the energy used to do the work, because there'll be a large percentage of the energy input will be wasted as heat. Think of your car. You put gasoline in your car. The gasoline has lots of energy in the hydrocarbon carbon bonds of the gasoline, but you only get like 12% to 15% of the gasoline's energy to run your car. The other 85% is of that energy in the chemical bonds is wasted as heat. So here we have it again in an equation form. The total energy input, I should have put, minus the wasted heat, is equal to the useful energy, also called free energy. The useful energy used for work, to do work. Okay, let's just review a little bit. Energy cannot be destroyed, but it can be dispersed into a less usable form. Yeah, that's called heat. Okay, the total amount of energy, according to the first law, has to be constant. So it would be stays constant. Now, useful energy decreases. So if you have a rock on top of a hill and you pushed it off, it can do a lot of damage to something that it falls on. It can crush it. Okay, so that's useful work. But then the most of the energy, even when you crush something, it will get hot. All that other energy is that was stored because the rock was at a height. We call that potential energy. All that energy, other energy, is lost as heat. So you might say, oh, the total amount of energy decreases because now the rock can't do any work on something. But it wasn't lost. A little bit was used to crush whatever it fell on, but the rest of it was lost as heat. Heated the rock, heated the object it fell on. But the total energy stayed the same. Okay, so that rock idea again. Here's the rock on top of the hill. It has a lot of stored energy, not chemical energy, but we call it gravitational potential energy because it's at a height above the ground. Now, when that rock is pushed and smashes into something, it does work on the object it hits. It crushes it. But a lot of heat is released, as I said before. Now, there's a lot of useful energy before the rock slams into the object it crushes. So, but that energy is gone now. I mean, it has changed into heat. So all the free energy that was stored in the rock that could be used to move something else, to crush something, that's gone. It's done its work, and the rest of the energy that remained turned into heat. Once you use free energy, that's all she wrote. So the free energy has decreased, but the total energy has not decreased because the free energy plus the heat that was released is equal to the original energy that the rock had. When it was off the ground on top of the cliff. So free energy is a measure of useful energy. Energy that can be used to do work. Useful means it can do work on something. Move it. Okay, when they use the word entropy, I'm just going to use instead useless heat. Useless energy or heat. So entropy is just a name I don't want to be using. So what if I word this question? A piece of wood is burning a campfire. The total amount of useless energy would do what? That would increase. The chemical energy in the wood input, some of that is turned into light. But basically, the light turns into heat as well. So all that chemical energy turns into useless energy, heat. Now you might say, it's not useless, it's keeping me warm. Well, it is, but it's not able to be used to do work. No. If you had, I guess, a tea kettle and it was on top of the fire with water, then that useful energy would be moving the water molecules, boiling the water molecules, moving them, and that steam could be used to push a turbine in an electrical generator. But if you're just burning wood in a fireplace, it's all that's useless energy. Heat, in other words. Okay, by definition, a catalyst is a chemical that speeds up chemical reactions. Okay, I'll explain this as we go on. It lowers the activation energy of the reaction. Hold on for that. By definition, a catalyst is not chemically changed. That's important. It doesn't react chemically with the reactants in the chemical reaction that is speeding up. Okay, more on what activation energy is in a few minutes. Okay, here's kind of an analogy to help you remember this. At this level, we have a rock. We want it to react. In other words, make it move to a lower level. But up here, it has higher energy because it's at a higher height off the ground than it does at the finish mark. Okay, so because you're higher, you can do more. You have more gravitational potential energy. But there's a hill in the way. Oh, if I just let that rock go, it would roll on its own if that hill wasn't there in the way. So I have to add energy to that rock to get it up to here so that it will roll down to here on its own. What a catalyst does is it lowers that lowers that energy needed to get it to the top so that it can fall to the bottom, to a lower position. So what a catalyst would do would be to make a smaller hill to get to where the rock needs to be. Take a lower path. Okay, so that will cause the reaction to go faster. Okay, so if we made this like an energy curve deal. Okay, here's the energy. We're plotting on the y-axis. And here's time. Okay, here's the energy of the reactants right there. And then here's the energy of the products down here. Okay, but there's a hill that you have to climb to get before you get to be the products down here. So here's the reactants, here's the products. Reactants, products. Products are produced, reactants are what the chemicals are before they chemically react. So let's say the product, in this case, the product energy is, let's say, 25 joules. Joule is the unit of energy that you use in chemistry. Could use calories, but we're going to use the metric unit. That's the reactant's energy, let's say, is 75 joules. And way up here, the top of this energy hill is, let's say that is 150 joules. Okay, the activation energy is the difference between the top of the energy hill and the reactants. That's called the activation energy. So it's the difference between, it's energy you have to put in to climb that hill before the reaction can go. So in this case, activation energy without a catalyst is equal to 150 minus 25. All you do is take the top energy of the top of the hill minus the starting point energy. Okay, so that would be 75 joules of energy would need to be put in to have reactants turn into products. Okay, what a catalyst does is it makes that hill smaller, like I said. Okay, let's say that the energy of the top of the catalyst energy hill is 80 joules. So that's the top of the energy hill that a catalyst would do. So the activation energy with a catalyst, with the right catalyst, will equal the top of that energy hill is 80 minus the reactants energy 75, and that would equal 5 joules. So the activation energy will only be 5 joules, much less. And so the reactants would react much quicker because it takes less energy to react now. So back to our model here. If we followed the sidewalk, like this blue guy's doing, pushing the rock up, I would get much fewer rocks to the other side than if the sidewalk was, if the hill was smaller. I would get much more rocks to the product side if the hill was smaller. So that's why they do this crazy analogy of a guy pushing up a rock. So once again, catalysts speed up reactions by reducing the activation energy hill from there to there. Okay? From this big height without a catalyst to this little height with a catalyst. Why are we talking about energy anyway? Well, chemical reactions either use energy or give energy. In living things, that's one of the characteristics of living things, is that they use energy. They take in energy, either like plants, solar energy, turning it into chemical energy, or like us, we take in energy in the food that we eat. The chemical bonds store energy in the food that we eat. We then break those bonds when we digest our food and release it. Really, we use it, or we transform it into ATP, and then we use it. It's all chemical reactions. And those chemical reactions need to be fast, quick. Okay, we talked about energy involved with chemical reactions with that example of the guy pushing that rock up the hill to get it to a lower location. Remember that? Well, anyway, this would be an energy graph for a chemical reaction. Energy is on the y-axis. And so where the reactants are in this graph, that's the energy of the reactants. And where the level where the products are is the energy of the products. And right here, the energy to the top of that energy hill is energy of the activated complex. That is the transition between reactants and products. The reactants bump into each other, and they're in the point of reacting. If they have enough energy to make a bond or break the bond, then the product will be formed. If it doesn't have enough energy to get to that point, that peak, it won't form a product. And the difference between the activated complex energy and the reactant energy, if those were numbers, you subtract them. That would be the activation energy without an enzyme. But if you do add an enzyme, you get a lower energy hill that you have to surpass. So that will mean a lower activation energy when you have with an enzyme, making the reaction occur faster, more frequently. So in short, enzymes increase the speed of reaction by decreasing the activation energy of the reaction. So you go from that height to that height with an enzyme. That's energy that needs to be input in order to react. Okay, enzymes have names, chemical names, and they tend to end with ASE. If you see ASE, the suffix ASE, after a word, it means it's a particular kind of enzyme. Examples: lactase, amylase, peptidase. These are all digestive enzymes. Okay, so here's a chemical reaction. Lactose, which is a disaccharide, a simple sugar made of 2 sugar rings, can be broken down into 2 monosaccharides, galactose and glucose. Okay, but this reaction is really slow. You need an enzyme, lactase, in order to decrease the activation energy and make this reaction go faster. Or else you won't be able, if you don't have this enzyme, you won't be able to break down milk sugar, lactose. So you'll be lactose intolerant, and you'll have to take some kind of pill that will give you the enzyme lactase, or else you're going to have stomach ache from eating cheese or milk or ice cream, because you can't break down the lactose. Amylase is in our saliva, and what it does is it breaks starch into smaller molecules of maltose, which is a disaccharide. That's why saltine crackers or those little oyster crackers in the cafeteria taste so good. They taste sweet because your saliva has the enzyme amylase that breaks down the starch into maltose and glucose. So amylase, we said, breaks down starch into maltose, and then other enzymes break down the maltose into glucose. Without the amylase enzyme, this would be a very slow process, breaking down starch. Okay, peptidases are enzymes that break proteins into their amino acids, smaller protein bits, and eventually into amino acids. So how does an enzyme speed up a chemical reaction? It does it by providing a space so that that the substrates get caught in, and so that when they bump into each other, they're more apt to make a bond or break a bond, depending on what kind of reaction it is. So if you can make the collision of two reactants when they bump together more favorable position, so that where they hit, a bond will form or break, then that will increase the chance of a reaction. And that's what an enzyme does. It provides a place called an active site for the reactants, which are called the substrates. Okay, the substrates fit in the active site. As they're bouncing around, they fit in the active site. So a collision between them will be more favorable in forming or breaking a bond. So it's improving the position of the substrate, so that when they do bump into each other, they have a better chance of breaking the bond or forming a bond. Here we have an enzyme, and here we have right here the active site. Okay, so A prime would be called the active site. That would be this region right here. And it has the shape of the reactants. Reactants, again, are called substrate. So the substrate molecules fit into the active site, as you see here. In this case, a bond will form because they're right in the right position for that bond to form. As soon as that bond forms, the new molecule comes popping out, and this whole molecule comes popping out, and the enzyme's ready to take on two more substrates into its active site. This is called the induced fit model of enzyme action, the induced fit model. And what that means is that as soon as these substrate molecules get into the active site, the enzyme will bring them together to form the bond, if the reaction is supposed to form a bond, or pull them apart to break the bond by changing the shape of the enzyme a little bit. So once the substrate is in there, it causes the enzyme to make a little shift in its active site, causing a chemical reaction to occur. So in this case, we got the substrate, and the reaction is going to break. It's going to break the substrate into two smaller parts. So it's This could be a disaccharide, for example, and it breaks it up into two monosaccharides. Okay, so the substrate will fit into the active site of the enzyme. Okay, this one, once it's in there, it's called the enzyme substrate complex. You could call it the activated complex at that point. Then what happens is there's a change in the shape of the enzyme slightly, so that it will either break the bond or form the bond. In this case, it will break the bond. So this is induced fit model, where in this case this would cause the enzyme to pull those two products apart. Then as soon as that's done, it releases them, leaving, and the enzyme pops back to its original shape, ready to take on another substrate. Now, notice that the enzyme is not really changing its shape overall or chemically reacting at all. Okay, let's look at this picture. I'm going to start with number one. Here's enzyme sucrase, and it has an active site that fits sucrose, a disaccharide. Okay, so sucrose fits in the active site. Randomly, it falls in there. These are moving everywhere, and it will fall in there, and it will bind to the enzyme because it's attracted there. Water will come in. This is called what kind of reaction? This hydrolysis, where water will be used and broken up and connected to the broken pieces of this disaccharide, in this case glucose and fructose. Okay, and this will occur because once the sucrose is in the enzyme's active site, the enzyme will cause that to happen by changing its induced fitting, change its shape slightly, and this will break the sucrose into its monomers, glucose and fructose. Okay, the energy required to start a chemical process, kind of a vague question, but if you think of it this way, here's the reactants. They won't go to the products unless you put energy into it. Okay, or it could look like here's the reactants and here's the products down here. It won't go to the products unless you put energy into it. That's the energy of activation. The easiest example I can think of a match. That match has a lot of chemical energy in it. The reactants have a lot of chemical energy, but unless you strike the match, you rub it on that rough surface, it's not going to give off that energy. So you have to add a little bit of energy to get the reaction going. That's called activation energy, EA. What happens to a catalyst in reaction? Well, nothing really. It is unchanged. It will change its shape during the reaction, but it will flip back to its original shape as soon as the product is formed. Why does a catalyst cause a reaction to proceed faster? Well, it does that by lowering the activation energy, not the reaction energy. activation energy is lowered. Biologically, with the high activation. Okay, so if you have a high activation energy, it's going to be a long time. It's going to be difficult to get enough energy for the reactant energy to go up there over the energy hill. So the higher the energy hill, the more unlikely the reaction will occur. So it will go very slowly without an enzyme to lower the activation energy, which if I acts as a catalyst in the body. Proteins are enzymes. And these are always proteins. This is poorly written. So let me change another name for, let's cross out protein, for reactants that fit into an enzyme. A specific enzyme is, what name do you call them? The substrate. Enzymes won't only bind to certain substrates. That's true. They have a certain shaped active site that fits a certain shaped substrate. So for every chemical reaction, you need a different enzyme. That's a really important concept. For every different chemical reaction in our body, we need a different enzyme. And where are we going to get those enzymes? We make them. How? Well, the codes for all the enzymes that we need, the thousands of enzymes that we need, probably hundreds of thousands of enzymes that we need to make are coded for in the DNA, right? The enzyme, the recipes, instructions for making any protein, enzymes being a type of protein, are coded for in the DNA. Okay, an enzyme can be used over and over and over again because you don't use it up. So this is false. Metabolism is the sum of all the chemical reactions that occur in our body or cell. One of the characteristics of living things is that they obtain and use energy. It's chemical reactions that taking energy and change that energy to useful forms. These chemical reactions, again, together are called our metabolism. Our chemical reactions are related. They work together in what are called metabolic pathways. So to turn one chemical, let's say chemical A, into chemical D, it takes a lot of little steps. And each of these steps is a chemical reaction. Each chemical reaction is moderated by an enzyme, an enzyme specific to that reaction. So the whole set of chemical reactions that has a specific goal of making product D, let's say, has a bunch of steps leading to the final production of D. Each of those steps is a chemical reaction. Each of those chemical reactions has a unique enzyme that speeds it up. If one of the enzymes is not there, the metabolic pathway can't produce product D. Okay, there's two types of metabolic pathways, anabolic and catabolic. Anabolic, think of anabolic steroids. They build molecules, they make a bigger molecule. Catabolic pathways are like digestion, they break down big molecules into smaller monomers. Okay, anabolic build, catabolic breakdown. Anabolic pathways are also endergonic. They use up energy, they require energy. So, anabolic are endergonic reactions that require energy input. Now, all reactions require a little bit of energy input. We call that activation energy. But these guys, anabolic, the products are higher energy than the reactants. So that's what endergonic means. Between the products and the reactants, this is called the heat of reaction, by the way, when you get to chemistry. You go up, so that's heat is absorbed. I'm just not talking about the activation energy right now. It's the energy between the products and the reactants. If it goes uphill, it's endergonic. Catabolic reactions are exergonic. And the energy profile graph has the reactions higher than the products. So the difference between the reactions and the products, the heat of reaction would be negative. That means heat's given off. Okay, so you should keep that straight, really keep all that straight. Anabolic, building molecules, requires energy. Catabolic, breaks down molecules, releases energy. Okay, once again, we're going to talk about anabolic. Anabolic builds molecules. The product is bigger than the reactants and has more energy. Once again, here's the reactants and here's the products on the energy hill. And to go from there to there, you need to input energy. Don't worry about this term entropy. Okay, here's a nice little picture showing what I just said. So here's the reactants, here's the products. It gained energy from the surroundings, and that energy is stored in the bonds of the product. That energy that was gained is stored in the bonds of the product. So a good example of an anabolic pathway is photosynthesis. Photosynthesis does not happen by itself. It's not spontaneous. It requires energy. That energy is the sunlight. Okay, so here's the reactants, and here's the products of photosynthesis. These have low energy. These reactants, water and carbon dioxide. But when a plant absorbs sunlight energy, it becomes energized with glucose. and oxygen. Okay? So, again, the reactants have lower energy than the products. You've built a bigger molecule than you had before. Anabolic. So again, catabolic pathways. You have large molecules breaking down into small ones, and energy is released. It's not, here's the reactant, and here's the products, and energy is released to the environment. These tend to be spontaneous reactions. We don't have to worry about entropy again. The products have less energy, they're simpler. So when we do respiration, we break down sugar using oxygen to form carbon dioxide and water. We balance it here. Okay, so carbon dioxide, glucose is a big molecule, and we're breaking it down into smaller molecules. So don't worry about this entropy business. So these bonds are being broken, and that energy is being released. So basically, the products have a lower energy than the reactants because energy has released. I just showed you that equation. Respiration is caused the opposite of photosynthesis, and that's what we do to get our energy from our food. And they popped in enzymes. Of course, enzymes are there. You don't write that in. You don't need to write that in. Enzymes are used for anabolic pathways as well. Catabolic pathways break down food. Digestion processes are catabolic, whereas anabolic pathways build up molecules. The whole purpose of digestion is twofold: to provide energy, the energy from the bonds that were broken, and to provide the atoms we need to build new molecules. And when we build our own molecules, that is an anabolic process, the opposite of a catabolic process. So we're constantly breaking down things and building them up to be our own. So remember, if a word ends in A's, it's an enzyme, right? So these are some enzymes that work with catabolic reactions, hydrolases. They break up water into H and OH. Remember that we use the splitting up of water when we break a bond in a polymer. That was called a hydrolysis reaction. Remember that? So the enzyme that makes that happen quicker is a hydrolase. Nucleases break down nucleic acids into their nucleotides. Proteases, we already said, break down proteins into amino acids. Lipases break down lipids into smaller units. Okay, synthases. Think of dehydration synthesis reactions. Those things build molecules, remember? So enzymes that build molecules up are called synthases. And synthases catalyze anabolic reactions where polymers are built up. Another name for synthases are polymerases. It is building up a polymer instead of just adding something. Here's a bunch of other enzymes as well. You don't need to actually memorize these, but we'll probably talk about them at some point. I don't really know why they stuck motor proteins in here. Motor proteins move molecules and organelles along the cytoskeleton. They're not enzymes. I really don't know why they put that in there. Okay. A metabolic pathway begins with a specific molecule ends with a product. Each step is catalyzed by a specific enzyme, of course. Okay, what kind of reaction combines building blocks to form bigger molecules? Okay, that's anabolic. Well, catabolic reaction does the opposite thing, breaks down. So anacata. Okay, to build up, you need to input energy, absorb energy. Catabolic means breakdown. When bonds break, they release energy. Okay, which is not anabolic, so it's catabolic. So basically, that's how you think about this question. If it's not anabolic, it's probably catabolic. So catabolic is breaking down to smaller molecules. Your bone's growing? No. Yep, nutrients in your food breaking down, releasing their energy. B is it. Growing? No. Growing means getting bigger. Exergonic means releases energy. So the reactants have more energy than the products. On an energy versus time graph, we can show that. So energy is released. These reactions occur spontaneously, even though there is a little energy hill that protects, that prevents the reaction from occurring without a little tiny bit of input of energy called activation energy. But in exergonic reactions that give off heat, give off energy, the reactants have more energy than the products, and that's a spontaneous reaction. Energonic reactions, on the other hand, energonic require energy put in. This picture down here shows an exergonic reaction because the reactants are higher than where the products are, a higher height. Okay, but of course you have to put in activation energy, but you can see that the reactants have more energy than products, so to get from there to there, you have to release energy. Now, endergonic reaction is the opposite. The reactants have lower energy than the products, so energy has to be absorbed to go from reactants to products. That's not spontaneous. There has to be a big input of energy, and that would be part of the activation energy. Okay, that requires input of energy, as I said, and it's not spontaneous. Okay, right here they're talking about energy curves of reactions. So here we have the reactants a little bit higher in energy than the products. Right here is the activated complex. That would be the reactants in the enzyme just about to form that bond. So it's called the activated complex. They call it the transition state. Okay, you can tell me what kind of reactions this is, right? Reactants are higher than products. So this would be catabolic. Releases energy, meaning that it's exergonic. Again, they're showing that even if it's exergonic, you had to supply some energy, okay, to the activated complex from the reactants. That energy is the activation energy, but it's exergonic because the products have a lower energy than stored energy than do the reactants. And to review, you know that with an enzyme, you decrease the activation energy. You decrease it so that the reaction occurs much quicker. Okay, just review the energy of activation. Activation energy is from reactants to the activated complex. And so that would be whatever this is. And this would be called the heat of reaction, delta H. They're calling it E2. The energy released or gained by the reaction, in this case is lost. So from the reactants to the products, that's the delta H, and we can see that's negative because it's the products minus the reactants would be a negative answer because the products is a smaller number. Then the reactants, a smaller number minus a bigger number would mean a negative number. So delta H would be negative. The activation energy is the energy of the activated complex. You get that number right here. Minus the energy of the reactants, you get that number there if it was a graph. It's always going to be positive. And the heat of reaction would be the products energy minus the reactants energy. So we call that the heat of the reaction. And in this case, it's positive because the product's energy is higher than the reactant's energy. So this would be delta H, a positive delta H. That means energy is absorbed by the reaction. That's why it's endergonic, not exergonic. And again, these do not happen spontaneously. Whereas exergonic ones do happen spontaneously after you put a little activation energy in there. Okay, let's look at this picture. What kind of reaction is this? Well, you got the reactants. Here's the energy of the reactants. Here's the energy of the products. Which one's higher? The energy of reactants, so energy must be lost to go from reactants to products. So this is exergonic. This right here, from that energy level, the products minus the reactants energy is that the heat of reaction, and that's going to be negative. That's this difference between those two levels, the reactants and the products. Here's the activation energy with an enzyme from that peak of the activated complex to the reactant level. They did this one wrong. The activation without the enzyme would be from there to there. They did that wrong with that arrow right there, so I'm going to erase that. So with the activation energy without an enzyme is much higher. That's activation without energy without the enzyme. Here's with enzyme. Okay, so this is an important part of this. This is something new. Again, I don't care about this entropy stuff. Now, if for endergonic reactions, the only one I gave you was photosynthesis, where the energy is supplied by the sun. Okay, but in us and in plants too, there's all kinds of other endergonic reactions that means energy has to be supplied for the reaction to go, absorbed, and that energy is from exergonic reactions that are coupled, that happen along with the endergonic reaction. So you got to power the endergonic reactions. Usually we use an exergonic reaction to power it, like ATP turning into ADP. So this coupling means using an exergonic reaction to power an endergonic one. So use the energy that comes off of this to power endergonic reaction. So this is kind of confusing. The exergonic reaction gives off energy that forms ATP. So exergonic reaction is losing energy that is saved by ATP. Is used to charge up ATP, the energy coin that's used anywhere in a cell to power things. And then that ATP reverts back to ADP, giving off the energy needed for the endergonic reaction. So, exergonic reaction gives off energy. The energy is saved. The energy is saved in the bond of ATP. Then ATP reverts back to ADP, giving off its energy to power an endergonic reaction. That's called coupling. Coupling. An exergonic reaction with an endergonic reaction in order to make the endergonic reaction go. Okay, the only problem with these reactions is this is delta H, not delta G. And they're showing that let's see, this would be an exergonic reaction because the products are lower energy than the reactants, and this would be an endergonic reaction because the products are higher energy than the reactants. So this would be a negative delta H, and this would be a positive delta H. Negative means it's released, positive means it's absorbed. Okay, respiration is an example of exergonic pathway, and photosynthesis is an example of endergonic pathway. This is just reminding you that every time energy is used by something, some of that original energy is lost as heat. That's the second law of thermodynamics. So every time ATP releases its energy, some of that energy has to be lost as heat. It's not 100% efficient. Okay, this is kind of an important fact. The difference in free energy, that's delta H. So, delta H again is that. It equals the energy of the products minus the energy of the reactants. In this case, it's negative. Exergonic. Okay, now, whether you use an enzyme, without an enzyme, the activation energy would be like that. And with an enzyme, the activation energy would be that. But whether you use an enzyme or not, that does not affect the heat of reaction. Okay, so that's kind of a concept question. Using enzyme decreases activation energy, but does not affect the heat of reaction. Again, endergonic reactions are coupled with catabolic reactions. Activation energy is not the heat release in a reaction, or that's delta H, so it's not that one. The energy given off when reactants collide, whatever that is. Who knows what that means? Generally, very high for a reaction that takes place. That's a lot worse than nothing. An energy barrier between reactants and products, yes. Here's the reactants, here's the products. Okay, you just can't go there. You have to go over a hill. An energy barrier. And that energy required is called the activation energy. What happens to an enzyme? Nothing. So Why does an enzyme cause reaction to proceed faster? It lowers that low energy barrier. Using an enzyme does not increase that activation energy. It doesn't cause different products. It causes the reaction speed to increase. More reactions occur in a given time with an enzyme than without. Reactions that are enzymes catalyzed always release energy. No, they could release energy, or they could absorb energy. You have enzymes working for both kinds, for catabolic and for endergonic and exergonic reactions. Enzymes are proteins, and the function of proteins depends on their shape. The shape of the protein. The shape of the protein will change if there's a drastic change in the temperature that it's subjected to. If you make it too hot, those enzymes will actually be permanently damaged. Make it too cold, the molecules that are bouncing around, the reactant particles, will go too slowly, and you'll have less of them moving into the active site. So, too hot, the shape changes of the protein, the enzyme, and it becomes non-functional. Too cold, and the molecules, the reactant molecules, aren't moving fast enough quick enough to get into the active site in the proper way. pH. You change the pH, and it changes the secondary and tertiary structure of the protein enzyme, and its active site changes shape and it doesn't function properly. Other chemicals will react with the protein and changes shape, make the enzyme non-functional. This graph shows the speed of the reaction. They say the rate of reaction on the y-axis. So way down here, the reaction is occurring really slowly. Up here, the reaction is occurring quickly. So every enzymes have a optimal temperature where that's the temperature where they work the best, where their active site is in the right shape for the reactants to enter, the substrate to enter. So too cold, you got low rates. As the temperature increases to optimal temperature, that would be our body temperature, those enzymes are in the right shape. They're functioning optimally at the best they can. Then you increase the temperature, and there's a sudden drop off where the enzymes are being denatured. That means the active site's being changed so that they don't even work. So the rate of reaction goes way down to nothing. Okay, so denature, losing its shape. You can see the active site right here has turned into a different shape, and so the substrate, the reactants, no longer fit. So the optimal temperature of bacterial enzymes is lower than our body temperature, a little lower than our body temperature. So if we raise our body temperature like a fever does, it denatures the bacteria, enzymes hopefully, and helps the white blood cells to kill, to clean up after the bacteria before they start causing damage. Now this would be pathogenic bacteria. So detergents contain enzymes that help break up stains, grease stains, lipases probably, lipases. But the enzymes have been designed so if you don't want to use hot water, which is expensive, you want to use cold water, you can buy detergent that has enzymes that have active sites that work better in cold water. The active sites if you use cold water tied with hot water, you denature those enzymes. If you use cold water with regular Tide, those enzymes don't work as effectively because the active site of those enzymes fit faster moving grease molecules or stain molecules. Changing the pH of the surroundings of an enzyme affects the way the interactions in the chain of the polypeptide chain of the enzyme. So if you mess with the way it interferes with the way the polypeptide chain is hooking up with the cell. Okay, if you mess with that, you mess with the shape of the molecule and you ruin the active site. Now, some enzymes work best at 7 pH, neutral. Some work best in acidic or lower than 7. Like we have enzymes in our stomach which work in very high acidic levels. We have very low pH levels. They're optimal pH. And then there's enzymes in our small intestine where it's alkaline, which work at high pHs best. Okay, so if I give you a graph like this, rate of reaction rate, how fast reaction goes, or rate of enzyme action, same thing. You should be able to tell me what the optimal pH is if they don't give you that right there. Okay, optimal pH would be between 4 and 5. They say 4.2, but it looks more like 4.5. If the pH is lower than that or higher than that, the active site, the protein chain loses some of its connections because of the H plus or OH minus in the solution, the extra, and that would change the active site. It would change the whole shape of the molecule and probably change the active site obviously as well. Okay, so this is really easy. You find the peak and then you go down, and that would be the optimal whatever. In this case is optimal temperature. That's optimal temperature. That's the best temperature that this enzyme would be working. Its active site would be in the best shape at that temperature for the quickest reactions. This one was optimal pH. You just go to the peak and you go down to read what pH it is. It's about 8. That's where that enzymes would have the best shape for its active site at a pH of 8. After over H and under H, the enzyme starts being denatured. That means its shape is being changed, therefore its functional active site becomes dysfunctional. Which enzyme has a lower optimal temperature? Duh. Where's the peak? The peaks for A is right here. Peak for B is right here. And so obviously A works better at a lower temperature than B. B is denatured at A. At what temperature do A and B have an equal rate of reaction? Well, that'd be right there where they cross. So it looks like, I don't know, it looks like 42 or something. Okay, the temperature effects shown in the graph. Okay, two enzymes, A and B. Enzyme A works best at about 35. Enzyme B works best at about 62 degrees, 63 or whatever. Each enzyme will function at room temperature. Well, room temperature is about 30 degrees Celsius. I mean, you don't have to know that because they have different temperatures that they work best at, so they won't. Let's see, 30. A would work, but B, no way. A would work somewhat. B would be totally dysfunctional because look at where it's optimal. A would be somewhat functional. B would be denatured. A wouldn't be denatured that much, but it wouldn't be as effective as it would be at closer to 40. So, no. Both enzymes are inactive at the freezing point. Freezing point 0 degrees Celsius, I would tell you that. That's totally true. Both enzymes has its own optimal temperature range. Well, that's true too. Both enzymes are the same optimal. Well, that's false. Each enzyme has its own optimal temperature range. Yeah. Right here is optimal for B, and this is optimal for A. So I would say both of these, B and C, are correct. They probably want letter C, though, because having two with different, they probably want C, but I would fight that both B and C are correct. I would defend that. Based on this information in the graph, which environment can you conclude as being more acidic, lower pH? Well, duh, the stomach enzyme, because it's acidic in the stomach, because stomach acids. So basic means greater than 7 to 14. So that would be this guy right here, C. C would work the best in a basic solution. B would work best in a neutral solution. A would work best in a acidic solution, less than 7. But basics, greater than 7. And so C would be the answer. The active site of an enzyme is the part where a substrate can fit. That's totally true. Yes, it can be used over, and of course is affected by pH, temperature, Okay, so 1 and 2 are my answers. Okay, so if this is the substrate right here, you can see that the active site right here doesn't quite fit it of this enzyme. So it needs something called a cofactor. So the substrate will go into the cofactor, and then the cofactor and the enzyme will fit in here, and the substrate will fit in here in the active site. And then the reaction will go. So this is the way you can have an enzyme around, and you can control the enzyme's reaction rate. I mean, the cell can, by having the more or less cofactors around. Okay. A cofactor that is an organic. Sometimes the cofactors are just ions, and sometimes they're organic molecules with carbon, and so they're called coenzymes. But I'm not gonna make a big deal. The word co means company working together. So here we see the cofactor right there, or coenzyme, and here's the substrate. Substrate fits into that slot, and the cofactor, which fits into the active site of the enzyme. Enzyme changes its shape, induce fit, right? And the reaction occurs to form products. Okay, there's certain things that slow down or stop an enzyme from working. Two types are reversible. That means they can stop it, and then something can be done to remove it, and then the enzyme's fine again, fine to work. But some are toxic poisons that ruin the enzyme. Doesn't change its shape. It just clogs up the active site by bonding with the active site, and that's a permanent change. It ruins the enzymes. Those kind of inhibitors, means slowing it down. Those kinds are irreversible. Okay, so here's the active site of the enzyme, and you can see this thing, this competitive inhibitor gets in. He competes for the active site with the substrate. Now that's not a permanent bond. He's just kind of in the way. He might be hydrogen bonded, which is weak bonds, slightly attracted to the active site, but it's keeping the substrate out. So it's slowing down the reaction that the enzyme's supposed to be doing. And the cell might want it to slow down by making competitive inhibitors and transporting them to where the enzymes are working. But that's a temporary thing. It's reversible. It's reversible. So you can wash out the competitive inhibitor, and the substrate will start fitting in again. Doesn't quite look like the active site fits the substrate though, but they should have made it more like fitting it like that. They should have made it more like that. So it looks like it fits the substrate. So okay, right there would be the non-competitive inhibitor site. But right here, a competitive inhibitor has clogged up the active site in both cases. Okay, so they kind of made a mistake in this picture. Here's a non-competitive inhibitor. Okay, so when he's not inside this other site, this is not the active site. This is a non-competitive inhibitor site on the enzyme. When he's out of it, the active site is in the right shape to fit the substrate. But when he gets put into it, when the non-competitive inhibitor hits the non-competitive inhibitor site on the enzyme, which is not the active site, then that will change this. That will change that shape to not fit the inhibitor, the substrate. So when the non-competitive inhibitor enters this other non-active site on the enzyme, it changes the shape of the active site and the substrate won't get in. Okay, again, that is temporary. You can remove the non-competitive inhibitor and the enzyme will flip back to what was there in purple before I changed it. Now, how's this compared to a competitive inhibitor? A competitive inhibitor will clog the active site. In a non-competitive inhibitor, there's a special site in the enzyme that will, taking a non-competitive inhibitor, a specific non-competitive inhibitor, that yellow blob, and change the active site like I showed in red. In the competitive inhibitor, the active site's never really changed. And the substrate is blocked from the active site because of the competitive inhibitor. The competitive and non-competitive inhibitors can be reversed. It can be removed and the enzyme's fine. So irreversible inhibitors form permanent covalent bonds. Not hydrogen bonds like the reversible inhibitors are attracted to the sites by hydrogen bonds. But irreversible can't be reversed. They are attracted, they'll bind with covalent bonds permanently to the active site. Okay, permanently inactivating the enzyme. And like I said, they're found in poisons, like toxins, that snake venom, and pesticides that we design to kill insects, but not people or animals or plants. And some chemotherapy chemicals do the same thing. We add it to a certain, doctors add it to a tumor. This is kind of poorly worded. Molecules that help an enzyme work better, I guess, are called cofactors or coenzymes. So we talked about them as, here's an enzyme, let's say. There's the active site. Okay. Here's a cofactor or coenzyme if it's organic. Here's the active site. And here's the molecule that needs to be the substrate, the reactants. Okay, that substrate will fit into there, and then that will fit into there, and then the enzyme will do its job, and the substrate will turn into product. Okay, there's two kinds that bind at the active site. There's irreversible inhibitor, and then there's the competitive inhibitor. The competitive inhibitor competes for the active site with the substrate. So that's the choice, because I don't see irreversible inhibitors in the answers. Non-competitive inhibitors are similar in shape to the substrates that bind at the active site. That's false. They don't fit in the active site. Let's say this is the active site. They fit in a different site. Let's say this is the non-competitive inhibitor. Here's the active site, and it fits not in the active site, but in this other non-competitive inhibitor site on the enzyme. So that's false. That shape does not fit. This shape does not fit in the active site. It doesn't compete with the substrate for the active site. The substrate fits in the active site and is the shape of the active site. So it's true. Okay, an enzyme has been inhibited non-competitively. Okay, so non-competitively means the inhibitor is not in the active site. It's in the non-competitive inhibitor site. So if this is the enzyme, let's say that's the non-competitive inhibitor site that has changed the active site from that, which fits the substrate, to when that connects in there, it changes the active site, the normal active site, to the ineffective active site on the left picture. So the substrate can't fit in there anymore. Okay, so enzyme will increase its activity. No, it will decrease. Once that guy gets in there, it will slow it down. It will increase in substrate concentration, will increase inhibition. If you increase this stuff, the substrate amount, it's still not going to fit. That's not going to do anything. The active site has been occupied by the inhibitor molecule. No, the non-competitor inhibitor site has been occupied. The active site has changed shape. So that's correct. Okay, non-competitive inhibition is sometimes irreversible. No, it's always reversible. So the answer is false. Irreversible inhibitors may be used as drugs or poisons. True. Chemo on tumors or pesticides or snake venom.